In our previous lesson, we talked about isomerism in alkenes, naming alkenes, and the physical and chemical properties of alkenes. In this lesson, we'll talk about other forms of unsaturated molecules, alkynes, which have triple bonds and will be linear, and aromatics, which will have continuous rings of trigonal planar atoms. Even though aromatics have double-bonded carbons the way we draw them on paper, they actually have electrons that are partially distributed across the single bonds as well, and react very differently. For this reason, we're going to define aromatics as their own functional group. Because alkynes have triple bonds, they will have an index of hydrogen deficiency of 2 for every time an alkyne occurs. The formula then is 4 hydrogens lower than you'd expect for an alkane, CnH2n-2 instead of H2n plus 2. On a short alkyne, we might start with a skeleton of butane, 4 carbons in a row, but we can really only move the position of the alkyne around in 2 positions. The first position gives us 1 butyne, and the second position gives us 2 butyne. If you're looking at these and trying to figure out where that 4th carbon is, you wouldn't be the first. But remember, alkynes are linear. Their carbons are going to be arranged in a straight line, and so they'll always be drawn that way when somebody else is drawing them. That location labeled 2, where the triple bond becomes a single bond, is therefore a carbon. The bond can't change from a triple to a single bond without an atom in the middle. And again, the triple bond transition should always be a straight line, since that represents the geometry of the molecule. In 2-butyne, both carbon 1 and 4 are linear from the alkyne carbons, so the whole molecule looks like a straight line. Alkynes, like alkenes, can't freely rotate around the triple bond. But that doesn't actually matter with alkynes because they're linear. If you put your pen down in the direction of the triple bond, both of the atoms that are connected to the triple bond carbons will be on the line no matter what. After 1-butyne and 2-butyne, we can't create any more alkynes as positional or skeletal isomers. But we can use our index of hydrogen deficiency of 2 to say that we could make 2 double bonds instead of a triple bond. And we can space those out on a 4-carbon chain as 1,3-butadiene or 1,2-butadiene. To get our other skeletons to actually work with an index of hydrogen deficiency of 2, the only other way is to either have a ring and a double bond or 2 rings. There is exactly one 2-ring 4-carbon molecule, and the name won't and shouldn't mean really anything to you. You can also have a cyclobutane and a cyclobutene and a 1-methyl cyclopropene and a 3-methyl cyclopropene. We'll continue to see the possibilities of functional group isomers dramatically increase the number of possible isomers that exist even for small molecules. It shouldn't be a surprise that our alkynes follow the same pattern that we had with alkanes and alkenes. First, the highest priority group is probably an alkyne at this point. Second, because the alkynes are our most important functional group at this point, both carbons of the alkynes will always be part of whatever chain of carbons we choose as a main chain. Third, because we are no longer dealing with alkanes or alkenes as the most important functional group, we change the suffix from -ane to -ine. Fourth, the alkyne will get as low a number as possible regardless of what the location of side chains are, just like with alkenes. And we'll always assign just one number for the alkyne, even though there are 2 carbons that participate in the triple bond. It will always be assigned the lower of those 2 numbers. And it can again be listed in 2 places, either right before the -ine suffix, as in but1-ine, or directly in front of the parent, as in like 1-butyne. The side chains are mostly the same as before, although it is now possible to get alkynes as side chains as well. We don't have special descriptors that apply to alkynes. If this all sounds pretty familiar, it should. The rules don't really change, we just apply them to a new functional group in each new time. An alkyne in the ring is not much different than an alkyne. We just change the ending to -ine instead of -ene. So on the left, we have cyclohexyne. Just like with alkenes, we don't need numbers because the alkyne is automatically numbered 1 and 2. If we do have another group, the group is numbered relative to the alkynes 1 and 2. So the molecule on the right is 3-methylcyclohexyne. If we had multiple triple bonds, we'll use the prefixes di, tri, and tetra, just like with multiple double bonds. There are multiple places that we can place this prefix, just like with alkenes, In this case, we could have 1,3-dibutine, or 1,3-butadiene, or buta-1,3-diene. Again, remember this is a 4-carbon chain because the carbons will always be drawn linearly coming straight off the alkyne. If we have double and triple bonds, we actually include them both as part of the suffix. We'd keep the numbers as low as possible for both alkenes and alkynes, but if we had to choose one over the other, we'd choose to give alkenes the lower number. With both alkenes and alkynes present, the numbers need to go right before the suffix portion they modify for clarity. So this would be a pent-1-ene 3-ine, but it'd actually be incorrect to move the numbers earlier in the molecule name. The alkene ene comes first in the name without the silent e at the end. The ine comes at the end regardless of the numbers associated with each. It's also possible to have an alkyne as a side chain. Why don't you start by trying to identify the main chain name? There are several correct names for the main chain, but each should have the pent-parent length indicator, the ine suffix, and the modifiers 1,4-di. Again, it's really important to remember that the end of the triple bond and the beginning of the single bond in an alkyne represents a carbon, even though they're drawn as a straight line. So now we look at the side chain. It's 2 carbons, which we've indicated with eth before. It's got a triple bond, which we've indicated with ine, and it's a side chain, which we've indicated with il. So this is an ethynyl side chain. In this molecule, it's attached to the 3rd carbon, making the molecule 3-ethynyl with one of those names. If we have a longer alkyne-based side chain, the form is the same, but we'd also need a locator for the alkyne, which is outside the scope of this class. So I'd pretty much only give you ethynyl. So now it's your turn to try some. Pause and try to name these molecules, and then we'll go over them together. The first molecule is a cyclohexyne parent. The alkyne is necessarily positions 1 and 2, being the most important group in the ring, which means that if we go counterclockwise, we can have the fluorines, indicated by fluoro, on positions 3 and 4. The fluorines are both on the same side of the ring, so this is a cis 3,4-difluorocyclohexyne. The molecule on the bottom left has 6 carbons. Again, be careful to include the carbons that transition from triple to single bond in your count. That molecule then is a 3-hexyne, or a hex 3-ine if that's your style. It's pretty common for students to want to give this a trans designation, but the carbons that are pointed up on the left and down on the right rotate freely, meaning that cis and trans versions are the same molecule. In the top right, we have an 8-carbon chain, if we count the top left to bottom right. The chain is some flavor of 1,7-dioctine. That puts the ethynyl group on the 4 position for 4-ethynyl, choose your own adventure. The final molecule is pentenine. If we number from the left, the numbers are 1 for the alkene and 4 for the alkyne. If we number from the right, the numbers are 1 for the alkyne and 4 for the alkene. Since the numbers are the same, the alkene is given preference for the lower number. So pent-1-ene 4-ine. Again, the physical properties that we're most concerned about are solubility in water and boiling point. Since we're still clearly in London force only territory, we will not have similar intermolecular forces to water and will still be negligibly soluble in water, just like alkenes and alkanes. The forces are weak, and boiling points will start out very low with short alkynes, but will increase with longer alkynes, just as the boiling points increased with longer alkanes and longer alkenes. As we pivot to start to talk about aromatics in the next slides, we'll see that they're also mainly London forces, and so are also largely insoluble in water and have low boiling points. Aromatics can have heteroatoms, that is, atoms other than carbon, which would typically increase the boiling point slightly and the solubility in water marginally, but not significantly, because they might have a small dipole. Speaking of aromatics, aromatics are a pretty interesting functional group because they look like they should be trienes, but they actually react very differently. This is because the electrons aren't just held between 2 atoms, as is typically shown in Lewis structure, but they're instead shared by every atom in the ring. We call bonds shared between more than 2 atoms delocalized. That makes the 2 structures shown equivalent structures. The one on the left and the one on the right actually are different pictures of the same molecule, and we call them resonance structures. Each resonance structure only shows part of the reality for a molecule. Sometimes you'll see the electrons in an aromatic system drawn as a circle instead of the double bonds around the ring, to represent that the electrons are shared around all those atoms. This would then mean the same thing as either of the structures above. Delocalized electrons are often much more stable than electrons held locally between two atoms, which makes aromatics particularly stable. But these delocalized bonds only get this aromatic stability if there are lone pairs or double bonds lined up for every carbon around a ring, or every atom around a ring. There are 5 aromatic main chains that I want you to memorize for this class, but they're all based on benzene, which is the simplest aromatic molecule shown in the top left. I'll show you the other 4 structures in just a bit. They'll all be on the same slide. Benzene has 6 carbons with alternating double bonds all the way around the molecule. Aside from being able to name benzene, you should also be able to recognize molecules that are aromatic, even if you can't name them. At this level, we should look for double bonds or lone pairs on every atom around a ring. So you need a ring, you need double bonds or lone pairs on each atom. This can happen in small fused rings systems like naphthalene, where all 10 carbons are part of a double bond around the outside, or anthracene, where 14 carbons around the ring are all part of double bonds. To be clear, I'm giving you the names here for naphthalene and anthracene so you know which molecules I'm talking about, not because I'd expect you to memorize naphthalene or anthracene. Aromaticity can also happen in distinct parts of a molecule, as in triphenylmethane, which has 3 distinct aromatic groups, but they're not all connected. Aromaticity also occurs in situations where non-carbon atoms are part of the ring. For this class, it's most important to recognize that nitrogens, which will often supply lone pairs that allow the rings to be aromatic, as is the case with adenine and cytosine, which are both bases that are used in nucleic acids. In fact, all the nucleic acid bases are aromatic, which also means that they'll be mostly flat. And this will play a particular role in the structure of DNA. So now that we've gone through examples of aromatics, let's play everyone's favorite Sesame Street game. One of these is not like the others. 2 of these molecules are aromatic. Which of these molecules is not aromatic? The first molecule, A, is not aromatic because the carbons on the top left and bottom right both are missing either a lone pair or a double bond. B is aromatic because it has atoms that participate in double bonds all the way around, as is C. It doesn't matter if there are different atoms, and it doesn't matter what else happens outside the ring, as long as there are either double bonds all the way around or there are lone pairs on places that don't participate in double bonds, it will probably be aromatic. Aromatic nomenclature is a little different than what we've seen before because aromatics are almost always the highest priority group, but will have specific names that need to be memorized. The specific names will imply the number of carbons in binding, and even which position should be considered number 1. Aromatics with 2 groups on them will often be named with special descriptors that indicate relative positioning instead of using numbers. Numbers are still acceptable, but you need to be able to recognize these relative positions. So we'll see all of these slightly different rules in aromatics, and then that'll be the only place that they really apply. So let's start out with the special names. We've already seen benzene, a 6-carbon aromatic with no substituents, that is, no side chains. If we have a substituent, often that substituent will define a specific name for the molecule. For example, toluene is just a benzene with a methyl substituent. Because methyl is part of the name toluene, the carbon that's connected to the methyl is automatically number 1 in the ring. Toluene is a common solvent. Styrene, as in polystyrene, the polymer of styrofoam, is a benzene with an ethenyl side chain. Ethenyl side chains also have the trivial name vinyl, which for this class is just trivia. Phenol has an OH connected to benzene and is important because it's an alcohol with special properties because of the aromatic. It's also part of one of the amino acids that's important for many enzymes. Similarly, aniline is an amine. It has an NH2 group, but it behaves slightly differently from other amines because of the aromatic. There are, of course, many other names besides these 5 names. These names are enough to give us a good working vocabulary for common and biologically significant aromatic molecules, so I'm asking that you memorize just these 5. Again, One of these 5 names will always be the main chain for any of the aromatic molecules that we name in this class. If we see a 6-carbon ring with alternating double bonds, we should check to see which of these names applies to the molecule to name it. So here are some examples. Starting on the left, we look at the molecule and we see that it has a chloro side chain and an ethynyl or phenyl side chain. Since that ethynyl group makes the molecule have this special name styrene, we give that group the 1 position and we make this a 2-chlorostyrene. Similarly, the OH on the next molecule makes this molecule a phenyl, and the OH is automatically 1. This molecule then becomes 3-bromophenyl. The third molecule is a 4-chloroaniline because of the NH2 group on top. And the fourth molecule is a toluene from the methyl group on the top. The NO2 groups, which we don't talk about in this class, are nitro groups. Even though we could have the numbers 1, 2, 3, and 5 if we numbered starting with one of the top nitro groups, the methyl is automatically assigned 1 since it's part of the name toluene, making this a 2,4,6 trinitrotoluene, or TNT for short. I also mentioned earlier that in certain cases, we'd have special descriptors that apply. These special descriptors, ortho, meta, and para, apply only to aromatics based on benzene, like the ones that we've been naming. These don't apply to other aromatics, and they also don't apply to non-aromatic rings like cyclohexane or cyclohexene. They can be used instead of numbers, but the numbers can also be used. For this reason, I'd recommend making sure that you can recognize and interpret the names ortho, meta, and para if given, but to default to naming molecules with the standard numbering system, because the numbers will always apply when done correctly. Again, our 3 descriptors, ortho, meta, and para, are just special ways of referring to the relative positioning of 2 groups. So anytime we have a group at the 1 and 2 positions only, we can skip the numbers and say ortho, or O, at the beginning of the name. Anytime we have a group at the 1 and 3 positions only, we can replace the numbers with meta, or M, and we can replace 1 and 4 with para, or P. In the last slide, we gave a bunch of perfectly acceptable names based on the absolute numbering systems. These were and continue to be correct names for the molecule, but we can also call the 2-chlorostyrene orthochlorostyrene, or O-chlorostyrene, and we can call the 3-bromophenol either meta or M-bromophenol, and we can also call the 4-chloroaniline para or P-chloroaniline. We can't give any other names to 2,4,6 trinitrotoluene since it has 4 groups. We can only use these relative numberings when we have 2 groups. So with all those limitations on ortho, meta, and para, why am I making you learn them? It's because you can't control how you are communicated to, only how you can communicate. So you should be able to recognize these when they are used, even if it's easier just to use the numbers yourself, and that again would be my recommendation. Four problems for you to try independently. Try to name them with both numbers and the ortho-meta-para relative positioning to see if you're understanding both systems. And pause before you continue. The first molecule is a benzene, since it only has halogen side chains. Chlorine gets the lower number because it comes first alphabetically, so we have 1-chloro, 3-fluorobenzene. Of course, if you use the relative positioning, it doesn't matter which is 1 and 3, and we replace both numbers with meta for meta-chlorofluorobenzene. Whether meta is fully written out or abbreviated, the name is actually still pronounced as meta. In the bottom left, we have a 4-bromostyrene, which could also be a parastyrene. In the top right, we have a 1,3,5-triiodobenzene. Because it has 3 substituents, we can't give it relative positioning. Finally, we have 2-fluorotoluene, or orthotoluene. That covers IUPAC names, the systematic form. However, some molecules, particularly aromatic molecules with complex side chains, are really difficult to name in this system, and so common names are used instead. I showed you this molecule on an earlier slide. Its correct IUPAC name is shown, and it's a doozy. I gave you the name triphenylmethane instead when I talked about it before, which makes the carbon at the center of the three benzenes the main chain and labels each of the benzenes as a side chain. Naming aromatics as side chains can make some molecule names much simpler, so this informal naming convention is often used. There are two benzene side chains that look very similar but differ only by one carbon. Both of these molecules could be named in IUPAC without too much trouble. But we can also use the informal way of talking about halogen-containing molecules, where the halogen is named as a main chain and all the carbons are side chains. Using the benzene side chain names are fairly straightforward in these types of molecules. The first molecule would be named as a phenyl chloride. Now notice that's not phenol, like with an alcohol on a benzene, phenyl, like with a YL, as a side chain. So this phenyl side chain is again a non-systematic naming convention, and it has a benzene directly connected to the main chain, which in this case is the chlorine. The second molecule is a benzyl chloride. The benzyl side chain is a benzene connected to a carbon that is then connected to the main chain, rather than directly connected to the main chain itself. And this is probably going to confuse some of you if you don't memorize these side chain names carefully, because the phenyl looks like a benzene, while the benzyl looks more like a toluene. So be very careful to make sure that you know that the benzyl, even though you would think it's the shorter molecule, actually has an extra carbon.